I
What
could
we
not
are
hear
trying to
that.
do here is bundling insurance with seeds and climate information services.
Drip is a simple, low-cost IoT water sensor that can be installed by anyone within 10 minutes.
You're not here.
Have you ever wondered what it would be like if a sensor was built to live in nasty wastewater conditions? We did, and we developed Sentry, a biofilm-based sensor to monitor the treatment performance.
IMIS is a tool for municipalities to improve FSN services. Accessible online, IMIS information includes location of septic tanks.
We dream of cities where no women have to worry about toilet while they are out.
Trackwater builds robots with optical and electronic sensor systems. They are battery-powered, never sleep, and cover the entire water treatment and delivery network from source to tap.
We are building bacteria capable of the rapid identification of COVID-19 virus in wastewater, allowing public health experts to generate real-time data on where the virus is spreading.
A digital twin actually also allows you to really improve your real-time operations by using data science and algorithms. Digital twinning is here and now and will continue to grow.
Welcome everyone to this episode 22 of the ADB Water e-marketplace. ADB, ADB Water e-marketplace is presenting innovative wastewater management technologies. My name is Jitendra Kumar Singh. My colleague call me JK. I'm a water supply and sanitation specialist at ADB. And we are here today featuring two of the treatment technologies. This e-marketplace is a webinar series that spotlights solutions. And today we have two technologies that go beyond the wastewater treatment. They also capture carbon. They provide recovery of water and other resources, including energy. To begin this session, I invite my colleague Lakshmi Sharma. She is the unit head of project administration at Water and Urban Development Sector Office in ADB. Lakshmi, we welcome you for the opening remarks. Thank you.
Thank you, Jackie. Am I audible?
Yes, perfectly.
Thank you so much. Good afternoon and welcome to this edition of the ADB e-marketplace. As you know, globally, we face multifaceted challenges in wastewater management. Nearly 80% of wastewater is discharged untreated into our rivers, lakes, and oceans. This undermines ecosystem, threatens public health, and adversely affects food security. In Asia and Pacific, the challenge is magnified by rapid urban growth, industrial expansion, and climate change. I like to stress also the increase in heat, which is really affecting the wastewater. For many cities, these factors are stretching the capacity of utilities, managing centralized wastewater treatment plants, which are already among the most energy intensive parts of the urban water cycle. These infrastructures are costly to expand and are difficult to sustain. ADB is actively championing transformative approaches, encouraging innovation in this area. At the ADB Water and Urban Development Forum Innovation Fair in May 2025, solution in wastewater management that go beyond treatment and also recover water and other resources, generate energy and capture carbon were showcased. In this session, we continue that conversation with two exciting technology that reimagine what is possible. Already mentioned by the JK about from the Algaesys, we will learn about the carbon negative solar power system that uses algae to treat wastewater while absorbing carbon dioxide and creating valuable byproducts. From Elefo Biotech, we will discover an on-site system that transforms toilet wastewater into clean, usable water. Practical, scalable, and built for the communities. Being a chemical engineer myself, I'm very excited to hear and learn from them. These innovations remind us that wastewater is not waste at all, but a resource waiting to be unlocked. By adopting smarter, more sustainable approaches, we can ease the pressure on our rivers and seas, strengthen urban resilience, bring us closer to circular water economy. On behalf of ADB, I thank our partners and all of you for being here. May this session spark ideas, partnership, and action to act. May this be a reminder that the solution we need are already here. They are not tomorrow's story, but are today's opportunity. And what's matter is how boldly we put them to work. With that, I'm delighted to welcome you to the discussion. Thank you.
Thank you so much, Lakshmi, for this warm welcome and setting the tone for the session today. Let's move on to the pitches from our guest presenters. First of all, we have Soner Bekir from Algaesys. He will present. And let me also remind you, all the audiences, to please use the Q&A section to enter your questions. And if you have any specific questions you want to talk, maybe we can arrange that. Let's dive into the solution pitches. Soner, the floor is yours.
Hi, JK. Thanks very much for the introduction. Hopefully everyone is getting that coming through now. Are you all getting that okay? The presentation? Perfect. So hi, everyone. I'm Soner Bekir from Algaesys. I'll be taking you through this presentation and introducing you to our proprietary sustainable wastewater treatment and resource recovery system. Firstly, it's important to state that we're powered by the sun, with solar panels for the minimal electrical components and directly with photosynthesis for the biological elements of our system. As a consequence, it's important to understand that wherever we deploy, we need unshaded sunlight, and we don't necessarily need mains power. So what's special about our technology? Well, it's actually a process rather than a technology. We've spent 14 years so far refining the design of the system to make it easy for anyone to maintain and manage, and to continually increase the energy efficiency and robustness of our designs. The basis of our technology is the ability to provide a perfect environment for our organisms to do what they do, as quickly and as efficiently as possible. We stress the organisms, resulting in them becoming hyper-reproductive, and as a consequence for us, they're hyperproductive. It's important to understand that we approach wastewater as a resource, and we approach treatment as a process that should not itself increase the impact on the environment, but work to reverse the issues associated with climate change. We do not produce GHGs, global greenhouse gases, while processing water. We're a net absorber of atmospheric carbon dioxide. So apart from treating water and absorbing nutrients, which pretty much all biological systems do, what's special about our process? Well, we produce our own flocculant, taking EPS, algal biomass, and diatoms from the first treatment stage to create a flocculation blanket in our primary clarifier. This reduces the suspended solids in the water coming into the bioreactor and makes sure we get maximum efficacy in the tank. We also produce an incredible amount of free oxygen radicals in the bioreactor, resulting in the destruction of complex organics, hormones, and medicines. Finally, we do all of this with a hydraulic retention time of 4 to 8 hours, where most biological systems require days. And for those of you that do better with simplified process diagrams rather than just words, this is actually a representation of the process setup in Gingin, a case study we'll be talking about later, and a good basic example of a small municipal wastewater treatment system, where the intent is to reuse the wastewater in irrigation and where humans can come into contact with the water. So what you'll see on the left-hand side is the raw wastewater coming into the system, goes through a traditional fine screen where we take out any of the typically non-organic solids that can't actually be dealt with. Water then goes through a primary clarifier to a balance tank when we have the opportunity, if we need to do something to balance the water. It then goes from the balance tank into the bioreactor, and then from the bioreactor where we do our magic, let's say, it goes into the secondary clarifier, which takes out any of the biomass that's left over from the process that we've just put the water through. Then goes into another balance tank, through a media filter, and because this system's in WA, Western Australia, we have to hypochlorite dose the system between 0.2 and 2 milligrams of chlorine per liter, per kiloliter, sorry, in order to make sure that water that's going out and going to be used for recycled purposes meets local health regulation. So we're quick, small, easy to operate and quick to build, but we aren't the cheapest and we aren't the most appropriate for every situation. We won't do cold and dark because the energy input to counteract these conditions goes against our sustainability values. We probably aren't the right solution if you're looking to treat the waste of less than 50 people on average. But we will capture lots of data, have a 50-year plus operating life, and consistently treat water to reuse standards. We'll also auto-tune the plants to match conditions and provide engineering cover for all operators. And we always work with local suppliers. We will give you water and fertilizer for the lifetime of the plant. So taking a look at some of our case studies, we're going to show you two today. This one's Summit Lake. It's actually been operating for 11 years. During the week, there's typically 8 houses worth of effluent going into the system. And during the weekends and at vacation times, then you get somewhere between 350 and 450 recreational vehicles worth of chemical toilets being emptied into the system. It's managed by park rangers. In the 11 years of operation, it's actually never failed an effluent standard test, and we are continually monitoring the output of the system. It's only had a single plant failure in that 11 years, and that was caused by a direct lightning strike, which resulted in us having to replace the electrical board. It's still working on the original pumps and blowers, so it's an incredibly efficient and remarkably well operating site. Then we come to the current bane of my life. This is a system that I've been bringing into completion for, it feels like a lifetime, but it's actually just the last year. It should be fully operational in another couple of months. We've been severely held up, unfortunately, by the developer on site, who've created a number of interesting issues that we've either had to resolve or wait for them to resolve. It will service a community of up to 75 houses, and it should be fully certified by DWER, which is the Department of Water and Environmental Regulation, and DOH, so the Department of Health, by the end of September. The reuse is principally for irrigation on an on-site orchard and for the common landscape. While I believe the biggest focus of the ADB is going to be remote communities, our system is capable of dealing with agricultural and industrial waste as well. It actually all comes down to the magic ratio and what your use or what your reuse requirements for the processed water is. Our system is modular, so it's scalable from a maximum of 25 kiloliters per day to, for example, 5 megaliters per day. But importantly, it handles flow variation very well, as our Summit Lake installation demonstrates. That's why it's ideal for tourism sites where flow can vary massively. Power and expertise is hard to come by, and nutrient and pathogen-free water for reuse is important to protect the very environment that attracts the tourists to visit. It will also, of course, handle aquaculture, food processing, large commercial buildings such as airports, universities, stadiums, and a number of food and agricultural uses as well. So this is one of those piece of string questions that everybody seems to ask: how much does it cost? But here's an example. Bear in mind the following. We only provide the design, quality assurance, and commissioning services in terms of labour. We work with local resources for electrical, plumbing, and civil services. You can choose who you want to do the work. We just check it. We'll only directly supply the bioreactors or their design and the logs that go into them. All other components come from local suppliers and distributors. You can choose who you want to supply. We charge a 5% fee for an eternal IP license for every plant, and we can monitor and report on your plant continuously. We can train whoever you want to operate the plant. It is really easy. In fact, the lovely lady in that picture there is my wife, who I've trained to actually look after the plant in Gingin. So all of that said, the Gingin plant itself cost approximately 350,000 Australian dollars to build in rural Western Australia. That included all of the components, the labour and the plant itself. It did not include the sewerage network in the village, the power supply because they already had an existing solar system, or the shed that it went into because it was an existing building as well. There's an ongoing cost for that site of around about $500 per month for the monitoring and reporting system, and there's an ongoing cost of about $90 per month for connectivity. There's also an ongoing cost of about $160 per month for hypochlorite and actually for all of the testing kits that we have to use as mandated by Department of Health. The 350,000 includes a spare for all major components that may fail within the lifetime of the plant. So finally, the link to the intake form is on our website is actually really useful, even if you can't answer all the questions that the intake form has. You can just scan the QR code that's on the screen now, or follow the link, which will be available presumably in the published presentation. It essentially tells you what we need to know in order to properly understand a project. So we need typically to understand location, customer, the E. coli, coliphage, and Clostridia levels, the BOD, TSS, pH, turbidity, total nitrogen, total phosphorus, and of course the flow rates. While we appreciate there will be a lot of unknowns, the more we know before making a design, the better the design. That's it from me. Open to any questions.
Thank you, Soner, for this wonderful presentation. So we just heard about this carbon negative wastewater treatment plant running on solar energy. We have a few questions coming, but I must appreciate, Soner, that you already gauged what kind of questions will be coming. And when you talked about the cost, I was going to ask you what are the breakdown for this $750 per month, and then you took that also. So you're making us with less questions. But I'm one of the happy souls here to say that, you know, in this session, we have enough time to ponder over the topic, ask questions directly to the presenters who are the main person behind the technology. So let me start with this background, few questions which has come to me so far. First question is, what are the key enablers for the deployment besides financing? I understand you have partly already answered, but Soner, if you want to add anything here.
Sure. Realistically, we obviously need sun. There's absolutely no question about that. So if we're in the southern hemisphere, we need to be in an unshaded site, ideally north facing, so that we've got enough sunlight coming into the system to do what it is that we need it to do. On top of that, water temperature's an issue for us. I think the same for anybody that has a biological system. So any biological system pretty much stops working at around about 15 degrees centigrade. Ideally, if you can have water coming in that has a temperature of 25 degrees centigrade or higher, then it's the most ideal situation. And when all is said and done, that's one of the reasons we actually have the balance tank as well in front of the photobioreactor. It's to give a little bit of hydraulic retention time in that tank to allow the water to come up to temperature if it happens to be a little bit cold. And it's also one of the reasons that we build these environments in greenhouses. So actually we're creating as warm an environment and as protected an environment as we can for the biome that we're putting in there. So apart from the temperature and the sunlight, realistically, that's it.
Thank you. The next question which is coming is related to your case studies, which you talked about your experience in USA and Australia. The question is, have you done any projects in mid to low income countries?
At the moment, I haven't done any projects in mid to low income countries. We have done projects in Europe. We've done projects in, obviously, Australia. We're about to start projects in New Zealand. That being said, the projects that we're about to embark on in Australia and in New Zealand are being embarked on in First Nations or Indigenous communities that aren't what you might consider to be typical in terms of economic conditions, let's say, from normal Australian locations. So we're not talking about municipal wastewater treatment plants that we're replacing when we're talking about First Nations communities. We're actually talking about small communities, who are 250 kilometers away from anywhere, and who may have at one point 250 people in a village, and then at another point 8 people or 10 people living there. They're very nomadic in some respects and very seasonal. So whilst I actually haven't done this yet anywhere else, such as PNG or Indonesia or the Philippines, I think some of the places that we're looking at within Australia, although the climate might not be the same, the situation is probably pretty much the same as far as economic viability is concerned.
Great. We have one question, which is a follow-up to the previous question you answered. The question is, how can investment be recovered?
That will depend entirely on where it is and on what the system's being used for. So there are a number of commercial players that are interested in the technology. So by commercial players, I mean, for example, hotel chains. For them, the recovery part, or the cost-saving part, if you like, of the system is going to be the reduction in potable water that they're actually using for all of their operations. So for a hotel, we can put a plant on the roof, for example, because it's an incredibly low loading system. So we're not particularly heavy. And then we can process all of the wastewater from the hotel and give it back to them, losing around about 1.5% to 2% to evaporation. So they get a whole chunk of water back to the property that they can use for cooling towers, for washdown, for irrigation, for toilet flushing. And the biomass that we're producing, again, depending on the situation, it's useful right now, and the most basic reuse function for it is ultimately as fertilizer. It's an incredibly good fertilizer, and it's also a very good wetting agent. So if the soil is poor, then the algal biomass that we're producing is actually pretty good at doing slow release of everything that it's actually absorbed and also keeping the soil in good condition.
Thank you. There's one technical question asking what is the footprint needed for every cubic meter or say 1,000 liters of wastewater?
That's a really good question. Unfortunately, it's not a linear scale because there's only a certain size we go down to. But to give you an idea, a 50 kiloliter a day plant typically sits within around about 40 to absolute maximum 50 square meters of footprint a day. Sorry, 40 to 50 square meters footprint. So it is in fact pretty compact for a biological and especially for an algal system. We typically describe it as a constructed wetland in a tank, effectively, because we're getting around about 11 times the surface area within our tanks for treatment. So even though they're small, they're actually presenting a very large surface area for treatment.
Two of our participants have asked this question, which is relating to how the dissolved copper or algaecide inside the wastewater removed before treatment. In other words, it was put like, are there any contaminants that can kill off the algae, for example, metals, etc.?
Not that we've come across so far. I'm not going to say that there's nothing out there, and I'm pretty certain that if you put our system downstream of a herbicidal factory, then maybe, just maybe, the effluent that they were putting out would be enough to wipe us out. But I think that the case study with Summit Lake is actually a pretty good one because you're going with a huge amount of flow variation. You're going from, like I say, the effluent from 8 houses to 350 recreational vehicles in one go. But at the same time, you're also going from typical housing effluent where you're talking about showers and sinks and toilet flushes to recreational vehicle chemical toilets. So basically, when you're emptying 350 of the nasty chemical toilets that they typically have in recreational vehicles in America, you're putting in all kinds of stuff into that environment. And one of the reasons that the system is so resilient is because we're really stressing the biome and stressing it continuously, it's actually reproducing incredibly quickly. So it's not that the algae isn't dying off, it's actually dying off very, very quickly, but it's reseeding itself constantly. So as a consequence, even when it's getting a toxic shock, it's typically surviving without too much difficulty because of that high reproductive rate. And regarding the copper itself, and other metals that there might be, I honestly can't say if there are a bunch of salts that would turn around and cause a problem. What I can say is that where we have built systems and put them into places that have high levels of cobalt, for example, we get very weird algae forming in the environment that's black and globulous. Where we turn around and put these systems into the Pilbara, we end up with a lot of brown, chunky algae that seems to use the iron that's in the water to create its own sort of internal sunscreen. So it seems to be that there's a species of algae out there pretty much everywhere to deal with whatever the conditions are that we put it into. And because we're always using indigenous species, we're not making these things in a lab and just shipping them out to the environment. We're actually sampling from wherever it is that the wastewater is currently and using that to actually grow the biome that we populate the environment with. Chances are, if there's something that's naturally in the system, what will grow will be capable of dealing with it.
Sonia, there is another related question from Cesar, and that is, what about bleach? Won't it affect the system?
Bleach affects some of the stuff in the system. So bleach will typically affect the bacteria in the system, unsurprisingly. You know, yes, it can do. It will kill off a bacteria. In our experience, not enough that the bacteria won't quite happily turn around and reform and come back again. Don't forget that you're filling this environment with human effluent continuously, so there's normally not any shortage of bacterial load coming into the system, and it does pretty quickly reestablish itself when there are any kinds of issues with it. For it to be, for bleach to affect the system massively, again, you'd have to take a look and see what the flow for an environment was. And again, this is why I turn around and say the system is sort of designed for, a typical load, let's say, of 20, 30 people plus, rather than 1 or 2 people. So as long as you've got that flow of a reasonable amount of people actually going into the system, then you'd have to actually dump quite a lot of chemical for it to be at a concentration that would cause a problem for the system.
Okay, so I think it's time to go to the other side of the spectrum. The question is now on harmful algal blooms. What strategies are in place to prevent monoculture dominance or harmful algal blooms within the reactor?
Well, the monoculture dominance we deal with during the commissioning process, let's say. So when we establish the biome, one of the things that we actually do within the environment is make sure that the species that we have there and that the biome that we build up is what it is that we want to see. I'm not going to talk too much about that because if you like, that's our secret sauce. With regards to algae going out and into the environment, we're not overly concerned. And the reason we're not overly concerned, especially after 11 years of operation and having monitored the thing continuously, is that in the photobioreactor itself, we're producing a huge amount of oxygen-free radicals. And by a huge amount, I actually mean that typically we measure it as hydrogen peroxide presence, and then we're talking between 180 and 250 milligrams per liter of hydrogen peroxide in the treatment tank that's being generated automatically by the biome that's there. So when the algae is actually falling off and dying, it's also being sanitized pretty quickly, and any of the chemicals that are being released as part of the death of the algal, well, it's not bloom, but the algal species that are in there is being broken down before it can actually be emitted as gas or as chemicals within the water that's coming out.
Okay, Sunil, we are running short of time for the question answer. There are still questions, so I will request you to go through the questions when we move to the next page and if possible answer that. But I can take advantage of being a moderator. My question can still be put there. I have a question. I heard you 2 years ago that the perception mindset towards the biological treatment is still not picking up. So what is your take on that in last 2 years? Do you find it has changed or still picking up? Where do you think we are?
Yeah, we're getting there. It's been interesting the journey for the last couple of years. I mean, as you know, I'm a relatively new entrant into the water world, and it's taken me a few years to work it out. But the principal barriers that I've seen in bringing new technology is getting local scientific acceptance. It really doesn't matter to anybody what you've done elsewhere. What I've honestly seen in Australia, at least, is that if it's not certified by the Department of Health and if it's not certified by the Department of Water and Environmental Regulation, then people don't want to be the first, or at least they don't want to be the first for municipal wastewater treatment. So an awful lot of commercial users have less of a problem with it because their regulation issues, let's say, are slightly different. But the utilities themselves, and those are the ones that may even have the responsibility for the remote communities, they're incredibly risk averse. and they are not keen to turn around and adopt new technology until it's got a tick of approval from government. And we're right on the cusp in Australia with that. We're also there in the UK with the regulator there. And we're also there in Spain and Portugal now. So it's taken a couple of years to get to the point, but I believe that once all of the regulators and a couple of the stock listed utilities have started using our technology, that it will be a lot more prevalent.
Okay, thank you so much. This is a wonderful trend you shared with us. And with this, let's move to the next pitch. We have our next presenter, Rohit Kumar from Elefo Biotech. He will talk about Elefo CRT, which is having the capability of transforming the wastewater coming from toilet directly into clean water. So Rohit, welcome for your pitch. The floor is yours.
Thank you, everyone. Let me share my presentation to begin with. Okay. So I will be talking about a system that we have developed in past few years called Elefo CRT. The way presentation will go, we will describe how we see domestic sewage and how we have categorized them. And based on that, what we have developed is a system called Elefo CRT. We will be talking about how it is set up in a situation, then what is the technology behind it, something about its features, case studies, and also the available versions and cost. We have one slide on our company and then followed by our CRT development journey. Last would be how we can source it. So if you look at any sewage water, it consists of three components, fecal, urine, and water. And the combination of these three gives us something called three different cases. That's our definition. For example, in case one, which is typically community toilet and some public toilets, you will see the combination of fecal, urine, and water in such a way that it is typically high BOD, high COD, and moderate in nutrient. Nutrient is basically nitrogen and phosphorus. But the amount of water generated per person in this case is pretty low. When we look at the case 3, this is typically schools, office spaces, and some public toilets where urinals are used more often than others. This will be high in nutrient, but low in BOD and COD. So these are two different cases to be handled differently. Finally, the third case that we see is typically what we see in residential building and housing societies, where even the bathroom water and kitchen water is mixed with toilet water. The quantity of water is high and urine and fecal matter is low. This creates a third case. What we are addressing through Elefo CRT is case 1, case 2. We have not started our trials for case 3, where we believe that similar systems will be able to handle much larger quantity of water. So what is Elefo CRT? It's basically a containerized wastewater treatment system. The setup which we see for this is basically connected to a toilet or sewage generating source, followed by a screen chamber and an equalization tank. So what our system will do, we will pump this water into the treatment system, and the water is tested and then recycled. If it does not meet our required parameter, then the water will be bleeded out. And the tech behind this is basically, this is a combination of anaerobic and aerobic reactor, which is on the biological side. Then we have a physical separation unit, which is ultrafiltration membrane. And then we have a chemical or ion exchange unit, which takes care of the various smell and nutrient part of the system. Now, any of these things is not working properly. For example, biological treatment system is not working properly because of some reason, like temperature drop is there. Say we have, like in Delhi, it goes up to 4 or 5 degrees centigrade. Then then the chemical side will take over and will do the same job what anaerobic side is doing. And the UF membrane is basically a physical barrier which prevents any kind of solids to pass through. Only dissolved solids will go in the permeate line. This is a very robust system which can handle very high BOD and COD loads. What are our key features? It's high quality, pathogen free, because ultrafiltration membrane is there, which does not allow any helminthova or a very little bit of coliforms to pass through. Easy to monitor because we are connecting it to IoT system, which has multiple layers of monitoring. It saves water through recycling. And of course, it is compact. So you manufacture it in the factory, load it on a truck and send it wherever it is required. Very easy to install. There are only three systems which can be, three pipelines which can be connected to the system to make it operational. It consumes very little energy. So the estimation is 1 unit per 1,000 liters of energy is consumed, largely in running some pumps. We can even provide energy through solar panels, but we will recommend solar panels to be put on the toilet complexes rather than on these this treatment unit. We can have different kinds of front-end inputs, like it can be used for schools, it can be used for offices, it can be used for hotels, etc. And of course, it can also be installed on the top of the toilet complex, provided the system has that kind of a load-bearing capacity. Some of our work in the past is what these couple of systems are running in Ahmedabad in India. Both of them are in schools, approximately having 600 students and staff. This is the smallest unit, 10-feet long container, which is sufficient for treating more than 600 students' waste per day. So on the picture on the right-hand side below, you can see there are only 3 points for connection. One is a sewage line, other is effluent line, and then the sludge line. On the treatment quality side, we have taken one example from a community toilet where BOD levels, COD levels were very high, and this was done in Khichadipur, Delhi. The results were surprising even for us when we did it for the first time. And this has given consistent results in all BOD thing for 1.5 years. We had issues in the beginning with the nitrogen, which was later on addressed. On the cost side, this is ex-factory cost. So there are 3 sizes of containers that we have. There's a 10-feet container, 20-feet container, and 40-feet containers. 10-feet containers are sufficient for 300 people waste per day, which basically translates to fecal uses of 300 and urinal uses of 1200. Similarly, for 20-feet container, it is sufficient for 700 people waste per day, fecal use of 700 users, and urinal uses of 2,800. And similarly, we have for 1,500 people waste treatment system with 40-feet containers. Ex-factory cost is 25,000 USD for 10-feet, 35 for 20-feet, and $46,000 for 40-feet container. If you, okay, there is something about our company. we were established in 2014. We will be completing 11 years next month. We have also established a company called Elefo Tech, which is basically focused on R&D activity in this case and also retains all our patents with respect to this particular technology. We are also largest provider of manufacturer and provider of anaerobic microbial inoculum to Indian Railways in the country, with plants in both south and north. We also operate few large toilet complexes and FSTPs. We extensively collaborate with DRDO, IIT Roorkee, IIT Palakkad, and we have worked in India and Nepal in the past. So if you look at how we developed this CRT system, we started with DRDO biodiesel technology, which is essentially a biological treatment system in 2015. Then we got into commercial partners with the Gate Foundation and took few licenses from US-based universities. And we started developing CRT system. Then in 2022, we started our own R&D work. And then we came up with a CRT system version 1.0, which you have seen in the case studies before. And now we are coming up with CRT version 2.0, which is completely automated. No human intervention is required except once in a month. And it can be monitored by individuals, both on the client side as well as from our side. So there is a continuous monitoring of the effluent water on a certain parameter. Not all the parameters are measured. BOD, COD, TSS are currently being measured. So if you want to source this system, how do we source it? We can source it by first calculating amount of water that is being generated from the system and what kind of quality it is generating. For example, if this water falls in case 1 category or case 2 category, we need to be informed so that we can make required changes in the system. Then the selection based on the volume of the water size can be selected. At the installation site, civil work should be completed with screen chamber, equalization tank, and platform for the CRT unit complete. And then Elefo team will transport and install the unit. We can monitor along with the client all the O&M activities of the system. Physically, we will be doing periodic maintenance once in a month. We plan to increase it from 1 month to 3 months going forward, but currently we will be doing it for 1. I can be raised on the given details, and that's it. Thanks for listening.
Thank you so much, Rohit. The clarity you provided in the beginning itself, how to Elefo see the sewage, that was really commendable. So we are open for question and answer, and we have few questions. Let me start with first question. For Elefo, how frequent should the UF membrane be replaced since the concentration of solids from the anaerobic reactor is expected to be high?
Interesting question. The way this system is designed, we don't let too much of a solids to pass through the anaerobic reactor. There is an inbuilt settlement chamber, both in anaerobic reactor as well as aerobic reactor portion, and that is drained frequently once in a month so that solids don't build up in the reactor itself. Second thing what we do before it goes to the membrane, there are 2 separate filters of various pore size, which helps in reducing the solid content for the next stage. And these filters are also auto cleaning. So basically, if you ask me, there are 4 stages of filtration in the entire process. First is settlement, then there is 1 mm filtration, then there is a 100 micron filtration before it goes to the membrane. So frequency, what we have seen and have been, we have not really ran it for 6-7 years, but 4 to 5 years is the expected timelines. We have run these membranes for over 2 years now, and we have not changed any of these membranes.
Okay, thank you. The next question is what government policies are needed for higher adoption of CRTs? Maybe the question is broad, but maybe we could like to hear from your side. How do you perceive that any government policy could be in favor of adoption of more CRTs?
Well, I think something is already being done in India. Uh, Government policies are extremely important because basically government should ask all all the waste generating agencies, whether it is toilet complexes or small restaurants or offices, to treat their own waste at the source itself, rather than waiting it to get into the city municipal line to be treated in the large STPs. So this has multiple benefit. One, waste will be treated and water will be recycled. Second, load on the existing STPs will come down dramatically, and they will have much more bandwidth to have a better quality treated water, which eventually goes into water bodies.
Thank you, Rohit. Next, please allow me to club two questions. One question is on, can you tell something more on the maintenance required? And second question is little specific, talking about the scenario in the schools, whether the examples you discuss in Ahmedabad were on government schools or not. If not, the question is, what is your advice for government schools where there is a limited budget or funding for the regular operation and maintenance? There is another sub question on that, is that the assumption is that from the schools, it will be less of feces, more on urine and water. Do you think this technology will be useful there or too? Sorry for putting
Yeah.
all together. If you can, please respond to that.
Yeah. So as far as maintenance is concerned, there are three levels of maintenance in this. First is cleaning of filters, which will be done regularly once in a month. And along with that, there is a desludging schedule, which is taken care online by opening certain valves, and everything is through gravity. So we will not be using any kind of a pump to sludge pump. So the monthly maintenance is cleaning of filters and desludging. Second level is once in 3 months doing CIP of the membranes. So basically cleaning of the membranes using certain alkaline chemicals, largely alkaline. The third will be the replacement of activated carbon and zeolite, typically somewhere around once in a month, once in a year, sorry, once in a year. But it will also depend on what kind of water we are treating and what kind of results our sensors are telling. So if sensors are saying that after a month, after a year, it's good, everything is good, then we will not replace it. Maybe we'll replace it after.
Rohit, could you reflect something on the... Rohit, can you hear us?
Yeah.
Okay. Can you reflect something on the budget cost, operation maintenance expense figure for a typical school?
Okay. Typically, it is 15% of the capex.
15% of the capex. Okay.
15% of the capex. Yeah. And on the school, so the case study that I have shown you, we have put up these units in 4 different government schools in Ahmedabad. These places are approximately 30 kilometers from Ahmedabad, and we have been running it for almost 18, maybe 20 months now. They have given us new learning because it is largely urine, fecal matter is very low.
Yep.
So in such cases, what we do, we design an anaerobic reactor of a much smaller size, and we increase the size of the aerobic section. And that is why it is important to know which case we are treating. If you are treating case 1, we will design anaerobic reactor much larger than the aerobic reactor. If it is a case where nutrients are pretty high, we will design aerobic much larger than the anaerobic. Not only that, at the same time, the zeolite that we use to capture nutrient, that quantity will also vary. So multiple things. So when we design it for case 1, a system will be different. When we design for case 2, the system will be different.
Okay, next question is coming from my side. The example of Khichadipur, Delhi, which you took, first question was coming to my mind, why BOD is so high, more than 2000 milligram per liter? And second, it is amazing to see the results coming like less than 10 milligram per liter. So what is your perception? Why BOD is so high there in that scenario?
Yeah, this site has been studied by a lot of people for a very long time. So a lot of independent people also went and did this study. See, BODs are high in these because this was a community toilet where half of the time systems do not work, and even if systems are there, they don't use it. So most of the time you are using a small mug.
Yeah, so it is concentrated much, yeah.
Much higher concentrated than the usual ones.
Okay, thank you. I think I'm going to put the last question to you because after that we have time to close it. Sorry. It's sludge primarily generated from biological processes, membrane filtration, or chemical additions. How do you manage sludge generated?
Okay, so sludge is basically biological processes where all the sludge is generated. Membrane doesn't let sludge to go out. So if you look at this picture, you will see a white color box next to the container. This is our filter. So whatever sludge comes, it passes through this sand filter, and sludge is, and this is all through gravity because this is on a higher platform. So everything is through gravity. So sludge is settled here, and the water passes through and goes back for retreatment, goes back into the tank. So in this way, we are collecting all the sludge in this tank, and we clean it once in a year.
Thank you so much. With this, we will move towards the end of this session. This has been a wonderful, only 2 presentations, lots of questions, and really we were enlightened. And we hope that today's presentation has sparked ideas how to use the tools and methods in wastewater treatment. On behalf of ADB and the entire ADB e-marketplace preparation team, I thank all the participants who have joined us today this session. Our next e-marketplace session will feature digital solutions for water operations, and that will be delivered in collaboration with UK Department for Business and Trade. A post-webinar survey should have appeared on your screen. Please complete the survey to give us your valuable feedback, how we can improvise further. And also stay tuned for the next e-marketplace session. We'll communicate you the session timing and day. Thank you so much again. We close the session.